In physics, we often deal with equations that look messy, non-linear, and seemingly impossible to solve exactly. But here's a secret: we almost never need the exact answer. Instead, we trade complexity for simplicity. And that's where the Taylor series steps in. It's one of the most powerful tools in all of mathematics, a way to approximate almost any smooth function using just polynomials. And it shows up everywhere. It explains why small angular pendulums swing like clockwork, and even how Einstein refined Newton's laws. In this video, we will explore what the Taylor series really is, why it works, and how it quietly shapes the physics of the real world. Let's break it down. Suppose we have a function of a single variable and we want to express it as an infinite power series. What should the coefficients be for this equality to hold? Well, try plugging in x equals 0. What we get is that the coefficient c0 must equal the function evaluated at 0. Next, take the first derivative of a function and evaluate it again at 0. We obtain the second coefficient. Then take the second derivative and evaluate it again at 0 to get the third coefficient, and so on. So clearly, the coefficient Cn is equal to the nth derivative of the function evaluated at 0 divided by n factorial. This is the so-called Maclaurin series. More generally, the Taylor series is defined as an infinite power series with coefficients calculated from the values of a function's derivatives at a single point. Specifically, if a function f of x is infinitely differentiable at point A, then its Taylor expansion around that point is given by this formula. Note that the Maclaurin series is only the special case of the Taylor series when A equals 0. Okay, that's enough formalities. Let's take a look at what it actually does. Consider the following Gaussian function. We can use the Taylor series to approximate this function, let's say around point 0. More terms we include, the better the approximation. But we can also do the approximation around different points. But here's the catch: the series doesn't always work everywhere. Consider the natural logarithm of 1 plus x and its Taylor series around 0. We can clearly see that the Taylor series represents the function accurately only within a certain region. This region is defined by the radius of convergence. It basically tells us how far from the center point we can go before the series stops accurately approximating the function. Beyond that interval, the series may diverge and completely fail to represent the function. Similarly, for the function square root of 1 plus x, the series only works within a certain region, the green region in this graph, and outside that region it actually diverges. There are also special kinds of functions whose radius of convergence is infinite. This simply means that the Taylor series converges for all real values of x. Such functions are called entire. Examples include polynomials, the exponential function, sine, and cosine. On the other hand, functions that are not entire, meaning they have a finite radius of convergence, include, for example, the natural logarithms, square root functions, trigonometric functions like tangent, and their inverses. Now that we have seen how Taylor series can approximate mathematical functions, let's look at how this tool shows up in real-world physics. A great example is Lennard-Jones potential, which models how two atoms interact, attracting each other when they are far apart and repelling when they get too close. The potential is given by the following formula. At first glance, this function looks pretty complicated, but here is where Taylor series helps. Let's say the atoms are vibrating around their equilibrium distance. That's the point where the potential energy is at minimum. We can expand the potential as a Taylor series around that equilibrium distance, r0. Notice the first derivative vanishes because r0 is at minimum. What's left is a quadratic approximation, just like mass on a spring. This is why near equilibrium, the Lennard-Jones potential behaves like a harmonic oscillator. That means a small vibration of atoms or molecules around their equilibrium positions can be modeled using simple spring-like motion. This is actually a key idea in molecular or solid-state physics. Another powerful example is, for example, Einstein's formula for kinetic energy. In special relativity, the total energy of a particle is given by this formula, where P is momentum, m is the mass of a particle, and c is the speed of light. This expression represents the total energy of a free particle, that is, the sum of its kinetic energy and its rest energy. To isolate the kinetic energy, we simply subtract the rest energy term from this expression. Now, when the particle is moving much slower than the speed of light, we can use the Taylor expansion to approximate the square root. Remember the Taylor expansion of square root of 1 plus x? Up to first order, it's given by this expression. In our case, x is equal to the p over mc squared. So applying the Taylor expansion, we get exactly the classical Newtonian kinetic energy. Once again, Taylor series serve as a bridge connecting relativistic physics with classical physics, and showing us that Newton's kinetic energy is simply the low energy limit of Einstein's more general theory. It shows that Einstein's theory doesn't replace Newton's, it extends it. When particles move at everyday speeds, much slower than the speed of light, the complex relativistic energy formula simplifies beautifully into the classical kinetic energy we have used for centuries. And there you have it. From the vibrations of molecules to the theory of relativity, the Taylor series helps us understand and simplify complex systems. I showed here only 2 examples where the Taylor series are used in physics, but there are many more. If you find this breakdown helpful and insightful, don't forget to like this video. Your support means a lot. For more cool math, physics and visualization content, make sure to subscribe so you don't miss any future videos. Thanks for watching, until next time.